going to switch to my presentation. And so I was kind of, so this is the beginning of my presentation. So I was kind of busy. So this is going to be a little bit a presentation described like this. So it's a little bit improvisation. And most of the interesting part is going to be here, which are code snippets. And I'll upload this presentation somewhere on the probably the MLT GitHub page. And this is a nice song, and I won't play it. I will just show the title. It's about plagiarism. Like, oh, don't play. Okay, so it's from Lobachevsky, and the main message of the song is to plagiarize, to be a good mathematician, but you should not do that. Definitely, the whole song is a joke. But I found this link. So most of this is Sage. So this looks like Jupyter, and it is Jupyter, but it's not Python. It's Sage math, and I already talked about Sage a little bit. And I found this Sage interactions, and this is the calculus section. I think there should be a go to interactions main page. Yeah, so I was looking like, okay, how to do these interactive slides, and this is approximately how the whole thing will look, but this is a GIF animation, so we will be actually able to move this little slider thingy and see how the whole graph changes. And when I was looking for how to do this, I found this nice page, and like, oh, they have examples, and oh, they have calculus as examples. Like, let's go and look there. And I found that most of the stuff that I wanted to do is already available here. So I will be showing some of these. And I actually did the first one myself because that one they didn't have. So the rest of the thing which I should mention is that basically what I plan to do today is simply to go through the chapter and then review all the parts which I thought were kind of difficult to read and kind of like maybe they need some explanation. So let's start with my first question, and please use the reaction buttons. How many of you know how to calculate the derivative? So if I say differentiation and derivative of a function, please click yes if you know what I'm talking about and you know all the things, and please click no if you don't. The good news is that most of people do know. Okay, so I have 7, 8 yeses and 1 no. 10 yeses. Okay, most of people know what differentiation is. Or how to do it at least. So now I'm gonna ask for a go faster or go slower depending on, so if you actually feel that you fully understand what differentiation is, then say go faster, and you know everything about it. You know what's different, or what does it mean to have the differentiation at a point, what is the differential function, derivative function. I always don't mix up the nomenclature. So, okay, a lot of people seem to know this. Okay, that's actually nice. Okay, then I'm not going to waste too much time. Okay. So I'm going to clear the responses. I'm not going to take too much time on derivation. Okay, I got the, I will give a very short introduction, and then if you don't understand what differentiation is, then ask in the comments and then we'll talk about it. Okay, but for now, I'm going to skip it. The next question is, how many of you know Taylor expansion and fully understand Taylor expansion? And I hope to get a little bit more no's here. 1 person, yes. 2 person, yes. Okay, Taylor expansion seems to be great. This is an excellent indicator. So I'm getting 2 yeses and 10 no's. So, okay. Oh, and I said I'm going to quote Pavitra. So the motivating example, so this is, I guess, public, so I hope you can see this. So Pavitra said like, hi guys, I'm drawing a blank, no, this is this it? Oh, about prepare for chapter 5. I have thought of calculus and linear algebra as separate entities to hate. How does one prepare for this mindset change of integration between the two? Like chapter 5 in MML book. So I already immediately gave this heart, rainbow, and unicorn because I was like, yes, this is the kind of motivation I need. So yeah, this is really, really nice. And actually, if you hate, I mean, know or understand the two concepts, it's not really that hard. So I think the funny thing is the harder thing is the differentiation part. And yeah, this is okay. And if you know that, then linear algebra just helps you express things really, really compactly and really, really in a nice way. Let me just see some things here. Okay, so let's start. Maybe let's start with this nice little. So yeah, if you have the difference quotient, then we can have, it will define the partial derivatives. And if we have the partial derivatives, it will, we just collect them in the Hessian and the Jacobian matrix. And you see that it's collected in. So basically the linear algebra part, this is what I was talking about, just helps it collect it in a nice way. So it's just an organization tool which makes your notation and makes your formulas really, really nice and elegant and small. So you instead of having like, oh yeah, you have derivatives going from 1 to m, and then you have all the inputs going from 1 to m, and then you write a huge table. Why would you write a huge table? You just write a matrix, and then you know that, okay, the matrix is a Hessian or Jacobian or something like that. And you can write all the things that quite a long process in a quite compact form. And then this is the Taylor series where most people said that, oh, this is a little bit tricky. And I will explain that. It's a very nice concept. Okay, so the first thing is this drawing. And so if you know what differentiation is, you probably understand what this is. But I did, for those people who don't know, did make this little thingy, and this is my original. I adapted this one, which I copied, but this is the main thing. So let's say that you have a function, right? So this is sine of x. So it's a this nice blue line, that's sine of x. And then you try to select a point somewhere. So for example, let's say, let's look at this point here, which is just under 4. So I'm going to set this x0 to, oh, this is going to be hard. Wait, let me redo that here. X0, it shouldn't be skipping too much. It should be just doing like this. Okay, this should be easy. Come on, X0. What? Wrong. Never do. Oh wait, this is kind of strange. Whatever. Well, let's say that I can. This should be somewhere here, right? Okay, I didn't look at this in too much detail, it seems. So, but this now so you should be looking at the black dot, and it's about somewhere around 0.4. And I think this is actually doing something like how far from in the whole interval, which is between 0 and 10. So yeah, then it makes sense. So this is, I should have converted this to say actually 4 instead of 2 or 5, right? Yeah. Because yes, I think that makes sense. Okay, so but the main thing about differentiation is that you want to approximate or find the tangent here. And here the tangent, I'm going to show you a little bit more difference. Here the tangent at this point, at the black point, is the pink line here, right? But if you do this thing, that you take another point somewhere near the black point. So we are looking at the tangent at this black point at point 4. So if you take another point, the green one, which is close to this the point which you're looking at, and you make it closer and closer, and this is what I'm going to do. So you're making it closer and closer, and as it moves closer, I'm moving this green point closer to the black one, and these two lines will be becoming closer and closer to each other. So this is differentiation. And when they actually become 100% close, this is still not yet 100% close, or they did not converge. And you can see the 2 points also didn't converge, or are not the same in limit. This is, well, this is almost the same. This is a very, very small distance, very, very small delta. Then you will get the actual tangent there if it exists. It doesn't always exist, but if it exists, you will get as a limit. And that's the whole point of differentiation, to figure out what this line is. And actually, differential or the tangent or the derivative of a function at a point doesn't give you the line, it just tells you the angle of the line. So this angle here, or actually the tangent of that angle, because you know that that line will go through this point, so you have that information. You are just interested in at what line, at what angle does it go through there. That's your information. That's the information which you are looking at. And then if you do this at every other point, let me show you like here. Yeah, so this is almost the same thing, but now I'm going to be moving x. So I don't know if you can tell what's happening. So now I'm going so backward. So now I'm moving this point. So this is approximately, so considering the full interval from 0 to 10, x is at the 21/5 of this interval, sort of. So it's somewhere here. And this is the tangent there. And if I move this point from the left to the left now, slowly, and then to the right, a little bit faster, you can see that the tangent here is moving. So this is, if you get the angle of this tangent for each point, then you get the derivative of a function, right? And this is called differentiation. And if you know, so this is the basic. This is what you have to know in the beginning. And after this, most of the things become quite clear. So a few things I thought that are worth mentioning is that when I went to the university, I was like, oh yeah, I want to learn programming, I want to make video games, I want to be, oh, I don't know, learn everything. Of course, they start, instead of teaching programming, they start teaching you math. And they're like, oh Jesus! And then you get something like this. And let me find some place to write. Then you get stuff like this, like, and this is the funny part, is that I had a student from high school who went to the same university that I used to go to, and he was complaining, oh my God, how stupid are the teachers there. They say that assignment, so like when you do in programming, like x equals 3.14, that's not equation. Well, and I said, like, yeah, that's not equation. So if you want equation, you are doing something like x equals 3.14, because this is an action, and this is a, well, sort of a question or a query. So is this true or false? It's a logical statement, actually. And so if you start doing mathematics, you get a little bit more used to stuff like this. And of course, it's written with one equation. So it says that x equals something. And then when you do something like this, so if you do something like x equals, I don't know, 5, then this is kind of a statement which is, so either one of them is true or none of them is true. And then you don't have this concept of time, and you don't have this concept of variables which change, or this concept of changing states in mathematics. So you kind of get a feeling that things are static in mathematics, but actually they are not. I mean, it depends. And the thing is that calculus is describing such things. It's describing such processes. So when you think about differentiation, you should be thinking about this process, which I described here, like an approximation of a tangent going closer and closer to the actual tangent, and then imagining, like, yeah, when it doesn't move anymore, when it's already close enough. And you shouldn't be thinking about this as one static concept. You should be thinking about this as a dynamic concept. Yeah. So this is, again, like, you start as a programmer, you think that things are dynamic and your state changes. Math teaches you, no, there's no time. You just have logic statements which are either true or false, and there's no concept of time. And then you come to calculus and you realize that, yeah, I mean, I didn't realize when I was studying calculus, but this is the really important thing. So whenever you're thinking about calculus, you should be thinking about some kind of a process. and some kind of an approximation and some kind of a, it's good enough. And the it's good enough thing here comes with the approximation of the function. So let me move here. And I hope this, I'm kind of, let's see if this works. No, wait, I need to restart the kernel and then go faster. Okay. So I'm getting to the Taylor expansion because that's most of what you were asking for. So the Taylor expansion is an approximation, but let's just look at the derivative. The derivative is a linear approximation. So what is the easiest function which you can think of? The easiest function which you can probably think of is a line, right? So this one, this red line here is way more easier to describe than this sinus here. And this goes on, I mean, imagine that it's not a sinus, imagine that it's something even more complicated. So yeah, this is way easier to describe. And if you look close enough here, you will see that, well, I mean, if you zoom in enough, there will be very, very little difference in this small region here between the sine and the line, the tangent. So this is kind of a very rough approximation of the function near the point where you are looking at the tangent, right? And then when you do Taylor expansion, and this is it, let's see if it works, then it's doing the whole thing a little bit further. And yes, of course, then everything breaks when you do live stuff. But why this should be running smoothly? Just one sec. Here. Okay. Let's see. I think I got the problem, and I will explain why that didn't work. Is this it? No, this one is it. Yep. Okay, yeah, now it works. Now not F2, F11, and let's hide the toolbar. Okay, so here, this thing is a Taylor approximation. And if you have some specific question about Taylor approximation or Taylor polynomials or Taylor series, then please feel free to ask. Okay, so this is the function, this blue line here, this is the function e to the power of minus x times sinus x, okay? And this little slider thingy here, this says how many terms of the Taylor polynomial do I want to include in the graph. And the Taylor polynomial is the green line, okay? So if I want just the first thing, just the first term, then it will look something like this. So this is the tangent at the point, and this is a linear approximation. If I say next, I say 2, this will be a quadratic polynomial, which, as you can see, approximates the whole thing quite nicely in this region, and the whole region where to us, it seems that the two lines are almost or identical or almost identical is now quite large. And the thing is that as I move this to higher and higher orders, that's it will be kind of closer and closer. So let's do next one. So to me, it seems that it's approximately the same until here, and it's all the same here to my eyes. Of course, mathematically it is different, but it's like close enough or good enough or very, very close. So this can be sometimes useful. So instead of having some kind of a strange function like this to compute, to have something maybe a little bit more simpler to compute. And if you push this long enough, you can see that it's the whole kind of interval that it's quite close. It's getting longer and longer, and it's getting a better and better approximation. Of course, you can also see the other thing, that this is not a perfect, I mean, it's not a good approximation of the whole function. So if you want to do something like machine learning with this, you don't actually do this in machine learning, you do something else. Because here at the end, it goes way off. This is just a local, very, very local kind of, but very good approximation of given functions. And you also have to know the derivative of the function. So this is all more kind of an analytical thing. So this is more kind of more something for theory. And yeah, this is something I actually wanted to add, like back home. Oh yeah, it should be just below here. So back home, when I went to the university, I went to university with quite, how should I say? So I went computer science, but it had quite a hard mathematics. So like they pushed, and they still push mathematics quite hard. And we didn't have calculus, we had analysis. That's like the math version of calculus. So calculus is for engineers and physicists, and analysis is the same thing, but for mathematicians, where you have proofs and all kind of things. And when we said like, okay, let's define the sine function and cosine function and the exponential functions, well, we didn't go the usual route, like the geometric interpretation and stuff like that. No, they said sine is this thing here. And if you look closely, this is already in Taylor series form. So it's some of the, if you expand this, then it will be missing every other. Well, actually, let's do some math, okay? I want to do some drawing. I like drawing. So let's start with this one, and this is kind of fun. I want to show using these two formulas, these three formulas, the equation that e to the power of x equals cosine x plus I sine x. You probably, this is Euler's formula. And so I want some feedback if you're interested in me doing this. This is something, so please do some yes or no. Okay, one yes. If you're not interested, then feel free to say no. Okay, no one is pressing no. Some people are saying pressing yes. I'm going to, okay, I will try to do this. This has been a long time, but it shouldn't be so hard. So the thing is that you start with e to the power of x, which is of course x, right? And you use this first definition here, which says that, okay, it says that it's sum where of k goes from 0 to infinity, and it's x to the power of k over k factorial. And you say, well, yeah, that's nice. And I realize that I'm missing an I here. Sorry, that's my example. So my error. So I'm going to do this. So this here says Ix, and I is the imaginary unit, the complex I. Okay. So if you write this out, this looks something like so. So for k equals 0, I'm going to mark, this is the 0th element. So this is going to be 1 over 1. This is 1 factorial plus Ix over, oh wait, this should be 1. Yes, this is 1. This is 1. And then let's move on. This is 2. Then it's x squared, but this is with the minus because it's I squared. And then you go 2 factorial, which is 2. And then you move on. This is 3. And this is going to be minus I x to the power of 3. And then 6 factorial. And then you go on, so on. And the thing is that if you look at this pattern, so this is a 1, this is I, this is minus 1, and this is minus I. And this pattern will repeat itself nicely. So if you take out all the even terms, you will get, so you can split this sum up in this way. So k goes from 0 to infinity, and k is even. And you write this Ix to the power of k factorial, right? Yeah, that looks about right. and yes, plus big sum k from 0 to infinity, k is odd, and the same thing. So these are the odd and the even terms, so you take them out. But so because you know here that k is even, you know that you will never have I here, okay, in the first thing. So you will either have +1 or -1, but you can write that down in this form, -1 to the power of k, where k kind of, so if k goes from 0, 1, 2, 3, then -1 to the power of k will be switching between plus and -1, right? So that's kind of a nice thing. But then you kind of change the index, so now you will be doing, so then you have to think like, okay, where does this, where will this be +1, and when will this be -1? So it will be -1 if k is divisible by 2, but not divisible, wait, am I saying this correctly? So let's write it down. So I to the k is going to be, and of course we know that k is divisible by 2, so it's going to be equal 1 if 4, yes, if yes. So if k is divisible by 4, then this expression is going to be 1. And you can, if you're not sure why this is so, yeah, if you have any questions, like you're not sure what I'm doing, then you have the action go slower, okay? So if you don't understand what I'm doing, then click a go slower thing. Okay, somebody hit the go slower, and then I would ask you to, oh, well, wait, no, Taylor expression words. Oh, okay, this looks nice. Taylor series, of course, yeah. 3 blue, 1 brown is always a nice thing to do. So, okay, I guess I hope this is the question here. Wait, just 1 second. I just realized that I had a quite important request. Co-host. Yes. Sorry, I didn't see Susanna's question or request. Okay, so how does this work? I'm going to finish writing this here. So this is if, and this is going to be -1 if 4 is not a divisor of k. Okay, so if you start exponentiating I, so you look like I to the power of 0 is going to be 1. I to the power of 1 is I. Well, no, sorry, I should be going a little bit back because I'm looking at only even numbers. So this is 0, this is 2, this is 4, this is 6, and this is 8. So this is going to be -1. And if you think about this, this is going to be +1. And if you think about this, this is going to be -1 and +1 and so on. So you can see that this is divisible by 4, this is divisible by 4, this is divisible by 4, and every other is not divisible by 4. So the ones which are not divisible by 4, it's written here, they will be -1, and the ones which are divisible by 4, they will be +1. So if you write down now k equals 0 to infinity, and well, I'm gonna cheat, and I'm going to just write down the cosine thing, and but now I'm leaving off the I from here because that I is already in this -1. So this is x to the power of, well, not k, because it's going to be 2k over 2k factorial. So if you think about this, this is good because you will have here for 0, this 0, well, no, 0, 4, and 8, you will have here k 0, 2, and 4, right? So if k goes through 0, 4, 2, and 4, the -1 expression will be +1, and you will have here these exponents. So the 0 exponent, the 4 exponent, and the 8 exponent. And if you look up here, these two always correspond to each other. So you have the same thing down here. So this will be basically this sum. And if you go through this with some modifications, well, the one modification here is that in this case, k is odd. And if you think about k odd, then you know that we skipped every other entry here. So we skipped the odd entries here. And in the odd entries, so when you have something like, I need some space on the blackboard. Wait, let's see. Here. So, oh, this eraser is not so efficient. Okay. So, back to drawing. So if you have I to the power of k, where k is odd, that means that you can always write I to the power of k as I to the power of, I don't know, some r plus 1, because this is odd. And then you can always factor this out like I times I square to the power of r. And this is going to be I times -1 to the power of r. And then you see like, oh, okay, there will be an I everywhere. So in this sum, you will always have an I. So you can factor that I out there. And oh, good, I removed the one thing which I actually needed. So let's add it back here quickly. And x 2k factorial, yep. And then plus, so I factor out I because it will be in every term of this sum. And basically I have almost the same thing as I had here. And this is k goes from 0 to infinity, and x 2k plus 1 2k plus 1 factorial. And if you again check the indexes, it will be good. So these will be the even indexes. And of course I forgot something. It's the -1 to the power of k, just as here, to the power of k. And you can see that I started off with x, and then at the end I end up with cosine of x plus I sine of x. And the nice point here is that you can actually do term by term differentiation. So if you know the Taylor expansion of a function, then you can do the differentiation like nicely, like term by term. So that sometimes can be useful. So there was one occasion when a colleague when I was a student that she heard that the other university, which is more like how do you describe it, to kind of more sciencey and the more engineering type of university? So I guess like MIT and Stanford or something like that. So I went to the more sciencey university, and the other somebody was from the more engineering type of university, and they couldn't solve some derivation or some, I think it was some kind of derivation with the L'Hopital theorem, and they were like, no, this is impossible, you can't derive this, and it seemed very hard. And then my colleague from my university who knew Taylor expansion looked at it and, oh, let's try to do Taylor expansion. And she said like, oh, okay, this is easy. And because every term just became 0 or something like that, it became almost a trivial problem. So this actually has some nice applications. But yeah, so this can be fun. What's this? This is, I think, for 3D. Okay, so let's move back to the thingy. Oh yes, okay. So this is what we defined. We talked about. This is the approximation of the derivative at a fixed delta distance. And well, actually, it's yeah, it's h, and then if the distance goes to 0, then you get the actual derivative. We talked about this. This is a nice thing. So if you have any questions, you should do these examples. These examples are quite nice, and you should see. So the tricks are something like yeah, if you collect stuff nicely, you will realize that most of the things tend to 0. So like here, you see that all of these things go to 0 except this one. And then if you look at this one, then you have your answer. And so, yeah, this is how the whole analysis things work. That you think about the whole process, like, okay, what will happen? And you should be always imagining like things are going somewhere. So things are going towards 0, but they're not quite there yet. So h is going to 0, but it's not quite there yet. You have all kinds of simulations which draw these. So for example, when you're doing when you're solving differential equations, you have this whole idea of doing the simulation and approximating things. Have I been talking so long? Because we kind of didn't get too far. Well, actually, let me just finish up quite quickly. So yeah, the Taylor series looks like this, right? So this is what it looks like. So this, if somebody is scared by this term, this is actually, you should just ignore this. And if you ignore this, you get x to the power of k, which you saw in all the drawings or all the whiteboard stuff which I did. This minus x0 is the thing when you want to do the Taylor expansion, not around 0, because if you're doing it around 0, then it's called the Maclaurin series, I think. Yes, yes, I think that this. I hope this is called Maclaurin. I'm not sure. Then you don't have this term, but the Taylor is a little bit more general. So you have this minus x, and it just moves the point to x0. So if you substitute x0 here to x, then you get 0 here. So then you have 0 distance, right? And the more you move away from it, the worse the approximation gets. So the further you are from the one point where the approximation is perfect, right? And then wait, let's see what was on here. Yeah, Taylor series. Let's move on. I think I should mention differentiation rules. So I'm not going to go too much into detail how you derive them and how they should be used, except maybe for the chain rule. And so the chain rule, this is the bread and butter of machine learning, and this is the most important thing from this chapter, I guess. And if you think about it, it makes perfect sense. So the one interpretation of understanding the derivative is if you have the function and you look at one point and then you look at that you want to get the approximation. So you look at the difference. If I take two samples from the function at this distance, how much will the function change? Okay, so I'm interested, how does this distance relate to this distance, right? So this is the whole thing about the derivative, and this is the chain rule is when you have two functions which are applied to each other, right? So you have x, and then you calculate f of x, and then you calculate g of f of x, right? And then this is written in such a way. So, and you're looking at the derivative at some point x of the composition of these two functions, right? So this is the f of g, so g of f is actually this, right? So the composition of g and f. So if you think about this and you know separately how g changes things and how f changes things, then you kind of have to multiply them together, because you are kind of combining the two the two modifications. So for example, if you have some here in this drawing, it looks like that at this point or somewhere near here, this distance is shrunk by half. So it will well, if you input something, then it will output something with half the length or half the size in some sense. And then if you have something else applied to this whole process, so let's say that this is your F, and then you have some G, which takes the output, which is in some sense this thing, and then, I don't know, multiplies it by 3. So in this case, the input will be this small, short interval, this interval here. It will be now here. And then you will have some other function, which will take here, and then, I don't know, maybe here. And I don't know, for example, multiply it by, so like if this was 1, then this will be like 3. So let's say that the length of this was 2, then the output length was 1, and then here the input length is 1 and the output length is 3. So then if you combine all of this, this is like, so the input was 2 and the output was 3. So how does this, what is, if you multiply this, so the whole thing will be something like this. I don't know if this makes sense. So the amount of change, so if you normalize everything to units, so how will it change like one unit of things? It will, the whole process, so this one will shrink things by a factor of 1/2, so it will multiply everything by 1/2, and this G, it will multiply everything by 3. So if you multiply the two, so 1/2 times 3 will give you this result, right? So that's kind of how the whole whole thing works. And clear all drawings. And yes, okay. I'm considering how much I should, I guess I didn't start at 0, with the whole presentation, so I won't finish at 45, but I don't know how much I will be able to skip, to condense into the whole presentation, because the next thing to talk about is partial derivatives. So all of the talk up to now was functions of type like this. Let me show you. So it was R, arrow R. So it was all like real numbers map to real numbers, right? So that was our function f. But partial derivatives come in if you have some kind of n here. So if you have an input vector, and this is the interesting thing, because if you have something here at the other side, so some kind of an m here, that's not so interesting, because you can think about the case when you have something here at the, if your output is m-dimensional, you can think about them just like having m different functions and then putting them together. So that's not so interesting. While if you have some input, some function which depends on n different things, that's a little bit more interesting, because they all get mixed up and you can't really separate them. The outputs you can separate, that's no problem. So the point of partial derivatives is, well, it's maybe shown here. So here, and this is actually not just partial derivative, it's actually directional derivative. You can have a little bit more general thing than just partial derivative, but I will show the partial derivative thing as well. So yeah, this is a function. What is this function? I don't know, I just blatantly copied this from the web page. It looks like it's this function, something with sines and cosines, I guess. Show surface. I don't know. I'm going to give you homework. Try to figure out what's the function. But the main thing is that the function is this see-through bluish thingy. That's your function, which has two inputs. So this is one dimension of the input. This is the other dimension of the input, and the height of of this, I don't know, flying carpet is the output. So how high? So here it's small, and here it's big, or bigger at least. And then the partial derivative is like taking this slice, and if you look at the slice, then you can see that, okay, here's the slice, and on that slice, the 2D function, where by 2D function I mean the function with the 2D input, looks like this if you slice it at this with this plane. But then you do something like, oh wait, actually I should be showing it here. It should be, what's half radian? It's 1.60 approximately. So this is not exactly, this is, so sorry, this is not really partial derivative. So the original, the first image was this orange line, where it went like on the one side it was going down and then going to the middle and then going up and then again down, right? But now I turned it approximately to 90 degrees. This is not exactly 90 degrees, and you will see why. And here it's actually more or less gray, gray, gray all the way. And if you look here, you can see that, well, yeah, actually it is. And if I turn off this, hopefully it won't mess up anything. And look here. So yeah, the red line, that's the intersection with the function. And because I think this is in radians, so it's 3.14, or I mean, yeah, pi would be the 100 and like half a circle. And if I want 90 degrees, then it would be half of pi. So I guess this is approximately it, but not exactly. So that's why you still don't get like the flat line, but I'm pretty sure that if I would get here exactly pi over half, then, and wait, let me try to do this. Where's the angle? Angle, label, angle, 2 pif. What's pif? Float pi, well, what's 1 pif? That doesn't sound right. Okay, I'm not going to try it, but I'm, as I said, I hope you understood, it was clear what I wanted to say. So I'm pretty sure if you get pi over half here, you would get a straight line, right? Okay, I think I messed it up, or it's just trying to work really, really hard. Yeah, no, yeah, I didn't mess it up. It's close to. So that's the directional derivative. So the thing is that if you look at the two functions which you get when you slice the big function, the two functions are very, very different. So if you look at in the direction of the orange arrow, then it looks like some kind of sine, and I think it is maybe sine or cosine. While if you look at it at the direction of the blue line, if it were perfectly 90 degrees angle, then it would be a flat line. So here it would be a very interesting derivative all the way, while here it has a zero derivative all the way. So this is the thing, that if you have a function with multiple inputs, depending on at which input you are looking at, the derivative of the function can be very, very different. And I just remember that I wanted to give you something like an example. What's the saddle function? You have saddle functions. This is a saddle function. So if you look at a saddle function, you can't really, so it's basically the derivative is exactly the opposite, because here the derivative is saying that this function is going down in that direction, while if you're looking at this other direction, you will get the answer that the function is going up. So it's very, very, how should I say, not trivial what is a derivative of a function or when you have multiple inputs. So this is what you get when you're talking about gradients. You just take every input separately, and you look at, so this is the sign for partial derivative. So if you have like the function f, and then you have, and yeah, you go slower or go faster, you can do always some response. Somebody's saying that go faster. I'm sorry, I probably should, but if you have some, so please feel free to give feedback. So I don't know if there's someone who doesn't know this notation, please quickly press no, because then I will explain it. Somebody's saying, no, you don't, there is at least one person. Okay, and it's, okay, so this is the notation. So you have the function, you're looking at function f, right? And please change to yes when you understand, okay? So you have the function f, which you're looking at, you want to find the derivative or partial derivative of f. And then these three symbols you add to it. So you have this, I think it's delta, or I think it's called partial or something like that. So partial and then partial. And then here down, you write the variable at which you are looking at the derivative. So you basically, what you do, you ignore all the other variables, and then you consider this function to be only the function of this x1, so the first variable. And then you look at the derivative of that r to r function, right? So basically you convert, so you have something like that. Oh, wait, I want to draw. So you have f. Your f has n inputs and one output. And then, so f looks something like x1 ... xn, right? And then you can say that, okay, I'm going to define, so how should I say this? So I'm going to define a function g of x, which is going to be f of x, and then x1 x2, sorry, x2, because this I put this x in place of x1, and then xn, right? So if you look at it this way, I didn't really do anything, but here g is not a function of x2 and the others, right? So it's only a function of this first thing here, so which used to be x1. And then this g, you can look at this g as an r to r function, not as an r to the power of n to r function. Is that a contour plot? No, that's not a, wait, contour plot. Wait, no, is it a contour plot? Sorry, this is, I will look that up. I will look at this. Okay, I wouldn't say it's a contour plot. So wait, let's go back to the book back here. Yeah, so you basically ignore, you consider all the other inputs as constants, and you do the or some kind of symbols or parameters, in sense that they are not the variable, not the input variable, but just some kind of a parameter which you will define later, and you don't care about them. So you actually treat them as constants, and you derive only with your first input variable, and in that sense you have an RR function. So from real numbers to real functions, real numbers to real numbers function. And this is the case that we were talking about in the beginning. And we know the definition of that. So basically you have something like, if you look at this thing here, so the partial derivative for the x, for x1, the first dimension would be this, the orange or a yellow arrow or yellow direction, and the function there. And in the y direction, it would be the blue arrow, and it would be this one. The original thing that was the, so that this is x direction, and this is the derivative in x direction. And if you rotate it 90 degrees, which is almost flat, that will be the y direction. I hope that helps with the partial derivative thing. So this whole thing that you can take any angle, that's a little bit extra. So that's not partial derivative, that's directional derivative. Partial derivative is like only taking one special direction, and the direction is the direction of one of the inputs. So you're just moving one input. So basically it's like some kind of orthogonal direction in some sense. Yeah. And then if you take, so if you have n inputs, then you have n partial derivatives, and you can put them all in a vector. And so it's, in this book they use a row vector, and it becomes everything becomes very convenient, and that's the gradient. And so for the gradient, you can use matrix multiplication in the chain rule. So partial derivatives using the chain rule. This is just separately. So this is not partial derivative. So you can, if you have partial derivative, you can treat it as simple derivation and use the simple derivation rules. But then things kind of become interesting when, sorry. then things become interesting when you have, wait, this is still just partial derivative. No, this is a full vector. So here you have x. So this means that this will be, the output of this will also be a vector. And the chain rule becomes interesting. And here the chain rule kind of becomes a vector multiplication, right? So it's basically just becomes very, very nice. And maybe this equation, not sure how we got gradient in partial derivative. Okay, so the question is, so the gradient is just putting all the partial derivatives in a vector, okay? So you have, for example, look here, this, okay, 5, 4, 5. And yeah, so I'm not sure actually if we should slowly switch to discussion, because, yeah. Okay, I'm gonna explain this, and then I say that over. I still have some other things to show. Susanna, please don't stop the recording, and then we'll see how much we can cut or not cut. And everybody else feel free to join and ask questions on Slack. Okay, let me just first quickly explain this. So this is the function, okay? This is f of x1 and x2, and this is how it's computed. So the first parameter square times second parameter plus first parameter times second parameter to the power of 3. Okay, so then you do partial derivatives. You do partial derivative by the first input. So you're looking at this function as if x2 was a constant, right? So if x2 is a constant, x2 stays here, right? You're just deriving x1 square, and x1 square is 2x1, right? And then you move on here and you see, okay, x2 is a constant, and x2 to the power of 3, it's also a constant. So when you derive, this x1 just simply disappears, and you're left with x2 to the power of 3. And then if you do partial derivative by the second variable, then x1 will be constant. So then x2 will disappear because this is a linear term, and then so the derivative of x is 1. So this becomes 1, so 1 times x1 squared. So that's how you get x1 squared. And the same thing, this is for homework, how you get this one. So you have partial derivative by the first variable and partial derivative by the second variable. So this is the gradient. This is the gradient. It's a vector. It's a row vector. The first entry in the row vector is the partial derivative by the first variable. The second entry in the gradient is the partial derivative by the second variable. So this one, it's the first one. The second one is the second one. Does that help? And the cool thing about this is that when you do chain rule, where is the chain rule? Here is the chain rule. Wait, is this the chain rule? Yes, it's chain rule. So when you do chain rule, so it's f, and this is kind of a tricky. So this is very, even for me, I got confused a lot here, because so this is something like, okay, wait, I have to write this down. So you have basically one input. This is going to be t, and it has two outputs. I'll explain this how. That's going to be, well, they're going to be x1 and x2. And then it has one final, so they are the input of, the final output is f. So if you look at it, if you look here, so f is a function which with two inputs, x1 and x2. But what they're looking at is having x1 sinus t and x2 cosine t, okay? So these two things here are sine t and cosine t. So that's why we have R2. So this is the output of this first mapping here. It's basically, they're actually two functions. So I'm not sure if this is the best notation which I put here. But then when you get these two outputs of sine t and cosine t, you then they're combined like this into a single output. So in some sense, this is like a 1, 2, 1 kind of a mapping. And then what you do is you go here and then you look at this. So here, this is the, this is f, so partial derivative by x of f. And then this is x partial derivative by t. And if it doesn't make sense, what is partial of x? So x is actually something like this. So x of t is, as I said, and this is, then I say that this notation is good. So it has one input, the t, and it has two outputs. So a vector, and now it's a column vector. Oh, somebody drew something. Thank you. Please don't do that. But I can delete, don't worry. And I mean, you're welcome to do, oh, thank you. Okay, no problem. So the output will be sine t and cosine t, right? So when you, Samantha, or what? Equation. Okay, so I'm going to erase this very big thingy here. And I'm going to stop now with the presentation part. Please keep on recording because I'm not sure if you'll have, but everybody else feel free to unmute and ask questions, and also feel free to ask questions. So I hope, Pavitra, does this help with the partial derivative thing? And in the meanwhile, I'm going to look for, wait, let me just check because, sorry, I'm, by default, my mind today is a little bit, great. So the thing is that if you see this, that if you feel that, oh, actually the whole thingy that all the chain rule and everything, it kind of fit together, but it's still confused about the chain rule. Oh, okay, so still confused about the chain rule. Did you understand the thing of, so the chain rule is when you have two functions and you know how much, okay, so the chain rule thing is, okay, so the chain rule, so she's asking if everybody should be on Slack and you should be seeing this. So she says that yes, she understands gradient, but she doesn't understand, still doesn't understand chain rule. The chain rule says, wait, let's I want to write down the chain rule. It says that something along like this, right? Yes, so yeah, it's actually good what I wrote down. So it's the derivative of x of f with respect to x, yep, and then it's the derivative of x partial derivative with respect to t, right? So this is the chain rule. The first function, so this is something like do you understand the simplest chain rule for the single input and single output functions, where, because in this case it would look something like this. We would have t as an input, and then we would be applying x to that t, and then we would be applying f to that x. And then if you want to do the derivative of this, then it looks something like the derivative of f at x of t times derivative of x at t, right? So it says that, so this quantity here talks about how much f changes things. This quantity here changes how much x changes things. So you can think about this as outer function and inner function. This is the f is the outer one and x is the inner function. So to get the whole amount or of how much the combination of two functions modifies the input, you have to multiply them together. So you have to look at how much the first function modifies the input, and then take that amount, and then look at how much the outer function modifies the input, and then look at it at this point. So at the inner function application point, how much the outer function modifies the input, and then modify them. I hope that helps. And the nice thing is that if you arrange everything like this, so if you arrange the gradient in a row vector and the outputs as a column vector, and here this is like nothing special. You have everywhere delta t, right? So you have everywhere derived by t, so it's just simple derivative. So basically it has, so you have f, which has sorry, no, you have x, which has multiple outputs. So you have x1 and you have x2, and this is your x vector, right? But this is actually a function, x of t, and these are also functions of t. And when you do derivative, you just do derivative per coordinate. So this is like, this is the trivial, the easy part. And the little bit more complicated part was the gradient, which you said that you understood. And if you treat things like this, then you have to just do multiplication here, which is going to be a matrix multiplication. This is like the whole thingy, like how actually when you combine two things you hate, you get something which you really like, because two negatives or negative times negatives is positive. And now you say like, okay, if I know a little bit of calculus and a little bit of linear algebra, and I know how to multiply matrices, the chain rule for functions which have multiple inputs and outputs, it will be basically become matrix multiplication. So the whole thing that you learned about matrix multiplication, it comes in really, really handy. I hope if you still have questions, please do ask. But in the meantime, as I said, my brain is not really functioning, so I'm going to have to Google contour plot, because my brain does not work. No, it's not a contour plot. Sorry. Yeah, I mean, of course, this is a contour plot. Because of the, wait, actually, yeah, I think I know what you mean. The second one, right? Because the other one, that is a contour plot down here. Oh, where is it? Yeah, so this one, the gray, this checkerboard thingy, yeah, that kind of is a yeah, okay, that is a contour plot. Well, sort of, I mean, but yeah, that's a contour plot, I would say so. Any point, feel free to post questions. Yes, equation 553. 553. Yes. Oh, this is nice. Thank you. This would have been more helpful, right? So yes, and this here is, this is a Jacobian, right? Because first you have the gradient, and that's so the gradient, where is it? Let's see some things. So the gradient, where is the definition of gradient? Yeah, so the gradient is a row vector in the case of having, so it's a row vector of n length when you have only one output. But when you generalize this, when you have multiple outputs, not just one output, then you have the Jacobian, and I'm looking for the Jacobian. If somebody knows where it is, feel free to post it in the Slack, but I think it's here. Is it? Is this the Jacobian? Yes. No. Yes. Wait. Yes, this is it. Okay, this is not going to be nice. Yeah. So if you, this is the Jacobian. So that's like the more generalized version of the gradient. So the gradient is for the special case if you have. Well, let me just jot this down. I hope then it will be more clear. And if I'm writing something incorrectly, tell me, because sometimes that happens. So if you have like the simple case, the r, then you have just like one scalar value f of x, right? So you don't really need anything special. So if you have multiple inputs, so this is the next thing, then you have gradient, which is something like delta f delta x1 dot delta f, or not delta, partial f partial xn, and this row vector. And if you have, so this is element of r one row and n columns. And if you have a general function in the sense that it's an n inputs and m outputs, then it will be a huge, well, not huge, it depends on how many inputs and outputs you have. It will be a matrix, which is, instead of 1 times n, it will be m times n, right? And so if you go by column, so every column will be gradient, I'm missing an R, right? Grad 1, and then dot, 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 and toop, 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 and then grad M. So this is everything just really, really nice packaging. And if you package stuff like this, everything will work out very, very, very nicely. And yeah, basically that's it. Jacobian, yes, yes, yes. So this is the same thing. So this is the gradient or the Jacobian. So this symbol is called, I think, the nabla. It's like the instrument, like the harp or something like that. What else? What else? Yeah, so this example here, it kind of felt a little bit hard, but basically I think I got it. So this is something like, okay, what you had, and this is time to show me, I think my last, oh yes, this is the last visualization. This is actually cool. So when you had a one input, one output function, your linear approximation was a 1D thing. It was a line. And if you have a 2 input function, then your linear approximation will be a plane. Something like this. Okay? So this is the end of the chapter, the multi-dimensional Taylor thingy. So now you have a 2 input, I think this is the function, something with sine x squared plus y squared times cosine y times exponential minus half x squared plus y squared, whatever. There's this function, and we are doing the Taylor, the multi-dimensional Taylor expansion thingy. So the derivative of something like, so the gradient actually, right? Am I saying this correctly? I think so. So this is what the gradient would produce. It would produce this red plane, which approximates this blue surface near this red center. And then you can do Taylor polynomial or Taylor series and have higher order surfaces approximate the whole thing. It's so now you can see it's not a plane, it's not a straight thingy, it's now a second order thingy, whatever that might be. I think it's written here how it approximates. No, that's the f function. It doesn't write the approximation. And then you can see that it gets better and better, because where these triangles tend to mess up and the rendering is not 100% accurate, you can see that it's a larger and larger surface where the numerical accuracy makes the thing as if it's the same. So you can see very, very nicely how higher and higher order Taylor approximation gets better and better thing. So this is kind of cool. This is the same example what we had with the line, but this is now with a 2D surface. So it's the same thing, but more dimensions. Not only that, there are 2 contributions to a scalar. Is there an intuition about magnitude of contribution from each input variable? Well, so the magnitude of the contribution from each input variable, yeah, so maybe this helps. So the magnitude of each input variable are the partial derivatives, right? So partial one, partial first, partial second, that's the contribution of one derivative and the other derivative. And if you want to get the combined contribution, then you do the determinant. And I just realized that, okay, we still have a few minutes, that the whole thing is very, very important because of, so this is the whole thing why we did it. Where is it? Where is it? Where is it? Automatic differentiation, right? So this is the back propagation thing. And sorry for not talking more about this, but this is basically the chain rule applied recursively. So So if you look at neural networks, they're basically something like this. You have a bunch of functions which are composed. So you take one input and then you apply the first function, the second function, the next function, the next function, and that's what you get. And to do back propagation, and this is a little bit tricky. So what the book explains here, it's not exactly what's happening, because they're doing kind of a, well, this part actually, yes, because you need to do by theta. So this is what you need in backprop. But later on, they explain this thing, which I think explains the whole thing way better. They do derivation by x, but you don't actually need to derive by x. You need to derive by theta, and it's a little bit hard to get the whole overview picture, but this kind of brings you a nice intuition. So assume that you have this relatively complex expression, but you have some sub expressions which repeat themselves. So for example, this x squared appears 4 times. So if you want to do a program, you probably want to name that x squared something, for example, a, and then you substitute where you need it, and then you look at the next expression. The next expression is x of x squared, which is x of a. You call that b, and you see that, oh, this appears here and here. And then your next expression is c, which is the sum of the previous two, and that appears here and here. And then you have 2 other expressions. One of them applies a square root to this thingy, which we just did before, and the other one applies a cosine. And then you combine those 2. And so if you get like what's this called, a computational graph of how you get this. And then if you go backwards on the computational graph and use the chain rule, you will get a really efficient algorithm to get the partial derivatives by each parameter. Here you don't have parameters. Here you have only the input. But so this is a really cool way how to compute the derivative of f. And in machine learning, and so you should look at this example. It looks very long and very hard, but actually it's so long because they do it in very great detail. So if you do it step by step, it should be very easy. And wait, what did I want to show you? Yes, there is another example which you should work through in the book, and it's the one with the loss. Yes, this one. So example 5.11. This is again chain rule applied. And here you have this one very simple function, which is just a multiplication by a matrix. And you have another function, the loss function, which is some y minus this result. Yes. And here it explains the chain rule, how it's applied. I was confused a little bit by this notation, but these are just indices. So this is row 1, column D, and here also row n, column D. So don't be confused with this. And this gives you a very easy explanation how you get to the loss function for a relatively easy least squares problem. And the thing is that, okay, yeah, this could be done more easily if you do some other approach. But if instead of having a really simple function here, which is the case here, if you have a more complicated function with multiple layers, and basically every layer is one new function, the whole process becomes way more nicer and cleaner and more understandable. And with this, we are basically out of time. So officially, I would like to close the session. And sorry, I couldn't prepare more and actually time myself to get everything on time. I hope you enjoyed the small little demos. I quickly just want to look at all the other questions. What may not be intuitive is why the chain rule of a function of a 2D input results in a sum. Yeah, so it doesn't, so the sum comes in when the output is 1D. So the sum came from one input, then intermediate 2 outputs, and then one final output. that's why the sum came into discussion. And I hope this wasn't so bad. So sorry for the improvised presentation. If you have any questions, please ask them on Slack, and I would like to close the whole session for today. Okay. So thank you everyone for coming. Thank you for listening. Thank you for the questions.